getting back into it. There we go. So it's Nano Hub. Oh, yeah. Up and running. Okay, welcome back. Hopefully the Thanksgiving break was like a welcome stop, check in, kind of refresh, maybe get some sleep finally, stop surviving on Red Bulls and Pop-Tarts. Pop-Tarts was like my grad school. Every night class I would get like s'mores Pop-Tarts and a coffee. It was like how I got to the end of those 9 p.m. night classes. But let's just jump into, all right, not grading scale. I want to go into grading. Just like quick check-in on where we're at. Hopefully assignments are all turned in, at least like modules 1 through 4. If they're not, this is the time to kind of like finish those up and make sure that you're back on track. And then participation, I'll send out another form. Well, on Husky CT, there will be another form for your final participation assessment. And that's based on how you feel you participated in the class, like who were you connected to, what was your learning community, and then how does this class apply to your career and kind of your learning goals. And then we can work on like module 5 kind of work. That's like extra credit. So module homework number 5 would be worth 30 over 4. So like just over 7 points on the final score. And then project number 5 is 40 over 4. So it's worth like 10 points final score. So it doesn't hurt to try it. If you like this kind of work and you want to try something new, it doesn't hurt to try. You won't get any chance to revise it, but it's only extra points anyway. Yeah, so that's where we're at. Logistic questions or anything else to start off? Yeah, and this week we can work on whatever you want. Like if you want to build module 5 stuff, we can take a look at that, like what are the mechanics of that. If you want to figure out like how do I take the work that I've done, turn it into like an engineering portfolio, we could look at like how to use GitHub to actually display, because this whole website is posted on GitHub and you can kind of copy paste the same workflow if you wanted to revise it and kind of show like this is what I know about the topic. Yeah, so if you're joining online or watching, check in, let me know.
Do you think you could look at the last question of homework 5? I'm going to start on that one.
Oh yeah? Oh, it would help. Yeah, and I think we went through this before the break, but it doesn't hurt. You have to add .md to that hyperlink. So I have to, that's one of my finals week projects, is fixing all the links that we found that were dead. Because they do exist, but they just slightly misspelled. So let's run down, straight down in the very last problem.
It was like the whole guitar string part.
Oh, okay. Yeah. So this is one of those that there's, yeah, let's jump into here. So the same problem is set up in the reading. So one way to do this is kind of like figure out, all right, what worked in the reading, and how do I work my way backwards from there. So I'm just gonna do like a kernel restart run all on this third reading. I don't need that one. And I hid an error somewhere. And for the homework, all right, so we're gonna plot some mode shapes and then create an animation. And then also audio display. So we're doing the whole gamut. This is taking a little bit to load. There we go. Does this make any noise? It makes noise on my computer. And then my simulated guitar string. Not exactly the guitar, like beautiful, like classical guitar sound, but with some good, with some work, you can filter out all that extra noise. But this is like the audio signal from like just choosing like a pickup spot on that guitar string. And that's what I'm trying to like turn into the audio. All right, so I've got all this stuff. In this case, I was using DY. My thought was, at least the reason that I was using DY for this is that I think guitar pickups for electric guitars are based on electrical current, and usually that's based on speed, like current. So the faster the guitar string is moving, I think the louder the sound. And this, yeah, that was my thought at least. I might be wrong about pickups. Maybe they're displacement based. All right, so now, so I need that DY. So I'm gonna come back up here. This is all like setting up some animation stuff. Here's like the actual time shot. So like looking at the string at every point in time. So we're trying to get back up to the point where we can run the simulation. And that is, so like the actual guitar simulation is kind of like, what's the length of the string, how much tension, what's the density, how many kilograms per meter, like how heavy is the guitar string. And then the eigenvalue problem that we're setting up is one big A matrix with the same K along the diagonal. And right now we're doing like 60 node kind of problem. So let's try this. I'm just gonna take these three, oh yeah, that copy paste. I'm gonna merge them all into one thing so I can copy it. And we want to look at 6, 30, 45, and 60 nodes. So let's just start off with like 6 nodes to begin with. and length is 0.64, mu is 1.14, and tension is 71 newtons. It would help if I import some linear algebra work. I think I can do this. So what I'm doing here is setting up a 6x6 A matrix, and then figuring out what are the natural what are the eigenvalues of that, which is directly related to my natural frequencies. So first 10 natural frequencies are like 194, 380, 544, and those are just these square root of those eigenvalues and then dividing by 2 pi so that I can get like frequencies in hertz rather than radians per second. And if I take a look at A, that's kind of ugly. Let's do 4 nodes. Still pretty ugly. I'm just trying to show, for the most part, it's this tri-diagonal matrix. So I have something positive values along the diagonal and then negative values along those 2 off diagonal parts. Go back to 6. And now if I want to look at the mode shapes, it's really the eigenvector is the mode shape. So eigenvalues are going to tell me what the natural frequencies are, and then the eigenvector is going to show me what the shape of the string is in that, if it's only vibrating in that mode. So in general, it's a combination of a lot of modes. So to start, I can just say, all right, well, show me I think it's that first V. And the first mode shape looks like a guitar string that is in that half sine wave kind of mode. And if I look at the second one, I should see a full sine wave. And I don't really, because right now I'm not plotting the boundary conditions, but it is, if there's an extra 0 on either side, it is I think I can do like pad to add some zeros. Pad with, I forget how to use pad. There we go. Yeah, I can pad it with, if I add a pad of 1, it adds a 0 on either side, just to like show what does the boundary condition look like. And then versus now, if I want to say, well, does the mode shape look any better with 30 elements? So now let's change this make n 30. So now K is this big 30 by 30 matrix, which I'm gonna hide. Not a big change in the numbers of like what are the natural frequencies. Like here 195 instead of 198, but it's different. So what you'll see is that they all start, those numbers all converge. Is that you keep adding more nodes, and every time you add more nodes, there's more natural frequencies, but the lower natural frequencies converge faster. So now whenever I look at the mode shape of that second mode, I get a nice like smooth sine wave. It's kind of cool.
So do you just want us to compare like one natural frequency then?
Sorry?
Do you just want us to compare like one natural frequency for all of the different the values that they're in, or do you want us to compare like the first few?
This one says calculate first and second natural frequencies. So yeah, I've done it for 2 cases and kind of like pointing and saying like, hey, look, it looks better, but let's do a side-by-side comparison, right? So we'll merge. Let's put this plot up in here. Let's just look at the first 2, 0 to 2. And the reason I'm doing that is like if I can do it once, I can create a for loop and do it as many or as different ways as I want. I'm just gonna comment out like longest time period. So I don't need it right now because I'm just trying to look at natural frequencies and then also what the mode shapes look like. And then I'm gonna merge this top cell in there too. So now I've got one big thing. Let's take it all. And instead of just doing one at a time, $630, let's just start small. So I'm gonna make n node guitar strings and keep increasing n, go 6, 30, 45. And it's gonna print out those first 2 natural frequencies. So that's a good start. And then it's also, I'm gonna try to just plot those eigenvalues and I'll pad them with a 0 on either side. And we'll look at that second one because that'll be the slower one to converge anyway. So now what I'm looking at, like 6, 30, 45, I can see 194, 196, and then 196. So it converges pretty quick. And then 380, 391, 392, and that one's converging a little slower, but it'll get there. When I start looking at these sine wave, like the mode shapes that I just made, right now all I'm doing is plotting the vector, so it's just the mode shape versus the index. Also, the amplitude of an eigenvector doesn't matter. Like if I multiply by 10 or multiply by 0.1, it's still the same eigenvector. So I need a way to kind of scale everything down and put it on the same scale. And I have this like dx value. So I'm going to take this and call it like, I don't know, Y mode, like YM, to say that that is my mode shape. And now I'll say that X is going to be an A range from 0 to the length of YM times that dx. So that now it gives me X is going to go from 0 to L every time, because it's going to match the same length as ym, and it's going to take steps of dx the whole time. Now it's looking better, but it's still kind of hard to tell, like, are they converging to the same result, because their magnitudes are different, like the amplitudes are different, but again, amplitude doesn't really matter here. So what I can do is say I could divide by that, like, max of ym, so it always goes 0 to 1, and that kind of makes sense for a sine wave anyway, because usually sines and cosines go from 1 to -1. Now I see, like, yeah, this is, all three of them are basically producing the same mode shape, whether you use 6, 30, or 45. And even as I keep bumping up those, go from 6, 30, 45 up to 60. And here, let's do this. Use some squares. Now we can really see, like, it's all, mode shape is accurately captured. Even for that first, like, 6 nodes, for that second mode, the mode shape looks pretty good. So we demonstrated convergence, always good step. Now if I want to make an animation, now I want to give it an initial condition. So I'll come back in here. I'm going to take that next block of code. This one's kind of setting things up so that the time steps are small enough that we actually get a result that kind of makes sense, because it's taking, like, that largest time step that we had found before and using that, or sorry, like how fast things, like the shortest time period, this, so 1 over, like, the largest frequency, so that we're not, like, missing things in the simulation. So that FN kind of gets used for those time steps. And now, instead of saying that y is going to have, like, some function, like, I don't need to set my initial y to anything, because it's all going to be zeros. But my and then my dy is also going to be zeros, but my dy of 30 is 50. So right in the middle, when I'm using 60 nodes, it's going to have 50 meters per second right at that center node. Oh, it would help if I had Hewn step defined, right? I mean, you can use any integration method you want, but Hewn step works. Wave equation not defined. That would help if I define that too. So pasting in that wave equation. Then it'll take a second to kind of get through all of those time steps, but it does give us something. But the question is, what did it just do? So we can try this one, see what this one looks like. Whole bunch of noise. But it looks like it's vibrating. So vibration's good. And then let's try animating. And the animation, animation I wish was easier to do, but it needs a whole bunch of like initial stuff. Like you have to set up a plot, and you have to set up an init function, like some function to like clear things, and then we need something to set that line data. So it's all these like initial stuff to like tell Matplotlib how to animate the plot. So I grabbed all that. I was just trying to like copy stuff over from the reading, and now let's see what that animation looks like. And again, it takes a couple of seconds, but what we should see is a whole bunch of like little squiggles that pop up and bounce back and forth. Not too impressive, just like bouncing a little bit up and down. But we can zoom in a little bit, because right now it's kind of set up for like large deflections up to 0.1 meters away, like 10 centimeters, but it's only moving probably a couple millimeters. So let's go back up, and we'll change this YLM to like 0.01. Well, let's do like 03. Waiting, calculating. Now we can see a little bit more like the motion that's going on. It's still not moving a lot, but do you know why it looks so squiggly like that?
I think because there's like all the different modes that are oscillating together. Or...
Yeah, why are there so many modes oscillating together? This one's like this, like it's not that it's, yeah, I wouldn't expect you to know this just from like being able to create a plot or kind of look at these eigenvalues, but it's like, have you looked at Fourier transforms before? Do you know what the Fourier transform of an impulse function is? That one, it's the sum of every frequency. So you have to have frequencies from 0 through infinity of like sine waves, combining all the sine waves. So when we said take node number 30 and give it a velocity, it was like giving it a tiny little impulse function on that middle node, which means every single, no matter how high of a vibration mode there was, they all got activated. So everything has a non-zero amplitude in its mode shape. So we're looking at the combination of every one of those modes. It was, yeah, kind of cool. It depends on what you want. If you want to see that in a simulation, then it's like, yes, that's exactly what I wanted. I wanted lots of squiggles. But if you're looking for a smooth guitar string vibrating, it's like, all right, well, don't give it an impulse. Don't like flick the guitar string. Maybe like deform it slightly, like how we did in the reading. Like maybe give it an initial shape and say like I pluck the guitar string and let it go. Now everything has a little bit more smoothness to it rather than lots of vibrations everywhere. All right, so now if we want to try to listen to it, we can grab this and we'll do the same thing. Listen to that dy. I think here, let's do like 5 or something. Makes noise. It should be. I don't have a very good ear for it. At least I don't have like a trained ear. But we should be listening to a noise that's somewhere like in this 194. Like that's what it should be sound like. So if you do have a good like trained ear, you might be able to pick that out. So there are a lot of steps, but it's not meant to be like from scratch, building all the answers. But really, like, this is that key equation in here, like setting up stiffness as T over mu of that dx squared for the derivative there. Yeah.
Question on, so it's module 5, but it's the reading number, the second reading,
Yeah.
and it's the very first problem going back to 1D steady state temperature, or temperature through a fin.
Okay. Yep.
My question is more on it's the setting up the equations. So if you scroll down, so starting with where it says number 2, where it says T7 equals negative H delta X over K.
Yeah.
So the equation above that, to derive that, I don't understand the very last part. So I get the heat transfer part, we're saying conduction equals convection.
Okay. Yeah.
So the heat transfer is equal in that way. And if you're trying to say at the very tip of the fin that the rate of conduction equals the convection, or the heat transfer through conduction at the end of the fin equals the heat transfer through convection.
Okay. Yep.
So at the very end there, where it says HA TL minus T infinity equals negative K dt over dx. Right. I get the H of T6 minus T infinity, that's the last temperature.
Yep.
At the edge, T6. Yeah. But then when it talks about conduction, you're going now T7, which is, I'm not sure what T7 represents, but then we're subtracting T5. We're taking two distances. We're taking T7 minus T5 instead of T7 minus T6. And I don't understand why and we're also saying it's over delta X.
So what we end up so when at this T0, it's kind of, we already know T0, T0 has to be T base. So that one is T base. That boundary condition is easy enough. But up here, we don't know what T6 is, but we know something about the derivative at T6.
Okay.
So that's what we're trying to do. So we set up another variable that is some T7 variable, and we don't need to solve for it, but based on the derivative, there's going to be this kind of fictional T7.
And where is T7, I guess is my question. Is it the same location as T6?
No, it's 1 dx further.
Okay, so if that's the case, then why are we dividing just by delta X, not 2 delta X, when we're taking that difference? Because you're seeing it showing, so why are we not doing 2 delta X? It's just T7 minus T5 over delta X.
T7, T5.
It's saying it's just 1
delta
X away.
Yeah, so
that's my confusion.
Yeah, you're right. It would be T7 minus T5 over 2 delta X, like that.
Yeah, but it's just showing over delta X.
But then this one, oh, T7, T5. Is it 2 delta X? Yeah. Yeah, I would think it would be a 2 delta X. I think you're right. Because it should be, the step size should be 2.
Yeah. And then my other question is, so let's say that test to change either way.
Mm-hmm.
If you're looking at the system of equations down below 1 through 6, why did we switch the T infinity and let's call it Ti? No, sorry, go up where you were before.
Yeah, okay.
So originally, when you're looking at the convective heat transfer, it's always Ti minus T infinity.
Yeah.
And if you can scroll up just a little bit, there's the governing equation that shows basically your conduction equals your convection. You go up just a little bit more.
One more.
Just a little bit more. Yeah, right there. So it's negative K pi r squared equals h2 pi r, and it's Ti minus T infinity. Okay.
Yeah.
Then when you rearrange the equation to get all of the T's on the left side, basically,
Mm-hmm.
so you multiply by delta x squared to the right, divide by negative K pi r squared.
Yep.
And then eventually you set it all to 0, so you move everything back to the left side anyway.
Yep.
The sign flips. So it's now T infinity minus Ti when you go to the set of equations down below. When I don't understand why it changed. Do you see how it flipped there?
That's just, it just multiplied both sides by -1 so that so that we end up with like more positive things.
But why? How is it being
Is that
multiplied
right?
by -1? Because if you look at the initial differential, if you
Yeah.
look at the initial differential, you still have T0 minus, yes, it's Ti minus 1 minus 2 times Ti plus Ti
Oh,
minus 1.
yeah.
So it looks like there's a sign change, because if you originally divide by negative K to the
Mhm.
right, you now have a negative on the right side. But then
Yeah, so
eventually
that
you move
would
it all to
flip.
the left, so it would become a positive. So those, I wouldn't think Ti minus T infinity would change sign.
Yeah. And that one.
Because I understand the mechanics of once you have this set up, how it solves, but it's more just actually setting the equation up and getting confused with the, I guess, the algebra.
Yeah. Yep. So get rid of 1r there. Get rid of pi.
Eventually you replace that with just an h prime, basically.
Yeah.
You replace 2h over kr with h prime.
Like that.
Yeah, eventually you multiply delta x squared.
Yeah, and then we can.
But again, in the system that's shown, the T infinity and Ti are switched. Unless the
And
negative
then-
from the K disappears at some point, because maybe we're seeing transfers in a different direction. But I don't understand,
Mm-hmm.
at least the algebra doesn't make sense.
Yeah, yeah. So plus. Because it should, I'm pretty sure that it is 2 plus.
Like I say, the only thing that can change is the direction changes.
Mm-hmm.
You know, if you're setting up the heat transfer, maybe it's instead of negative K, it's positive K, because now the gradient is the other way.
Gradient is the other way.
Because usually conduction, the gradient is always acting. Direction of heat transfer is a negative temperature gradient for conduction, because temperature is decreasing.
Yeah,
So maybe that's what it is.
maybe.
Can't exactly figure it out.
Yeah. I think there is. Okay. Yeah. No, we're at time. I'll take another look.
If you can somehow figure it out, let me know. But
Yeah, I am.
It's not the end of the world. It was unsolved.
Is it possible that this was a negative or no? I don't know.
So at least from what's shown there, it should be the other way around.
Yeah, that there's
But I don't
a
know.
minus sign missing.
Yeah, unless it's missing or was added or removed.
Yep.
Without being shown.
Yeah, something happened along the way.
Let me say this, I'm doing heat transfer now. We did a project very, very similar.
Yep.
So,
Yeah. Nice. Okay, cool. Thanks a lot.
Also, I sent you an email last night.